Hi, I'm Asaf, and I talk about our paper, Connectivity Labeling and Routing with Multiple Vertex Failures. And this is a joint work with Merav Parter and Seth Petty. So the framework we're interested in is called informative labeling schemes. And in essence, labeling schemes are concerned with assigning meaningful names or labels to the nodes of a given graph. And this is in contrast to the standard meaningless identifiers we usually associate with the vertices, say the numbers 1 up to n. And in some variants, we may also want to label edges, but for now, we'll stick with vertex labels. So this can be seen as a distributed graph data structure, where each node stores locally some small amount of information. And the meaningfulness of the labels is in the ability to answer queries of interest merely by looking at the local information stored at the vertices. So for example, if one wants to answer some query involving vertices 2 and 11 in the graph, like whether they are adjacent, connected, or what is the distance between them, they should be able to do so just by inspecting the labels of these two vertices without any other knowledge on the graph. And the point of the labels is to be short, meaning their bit length should be as small as possible. So what's considered short? Well, if we are allowed to have labels of n squared bits, then we can just write the entire graph inside every label, which gives a trivial solution to any labeling problem. And at the other extreme, just having unique identifiers requires log n bits. So this is about as short as we can hope to be. So a bit more formally, a labeling scheme consists of two algorithms. The first is the marker or pre-processing algorithm, which gets the graph as input and outputs the labels for the vertices. And these are bit strings of length small l, which is the primary complexity measure to minimize. The second algorithm is the decoder or query algorithm, which gets the labels of some vertices that were generated by the marker and should output some information about these vertices, like distances, adjacency, and so on. And crucially, the decoder does not know anything about the graph G, it only gets the information stored in the labels of the query vertices. So after this general introduction, I'll now explain the specific labeling problem that we care about, which is fault-tolerant connectivity labels. So here the goal is to answer queries of the following form. Given a source vertex S and a destination vertex T, along with F vertices x1 up to xf, which are considered faulty, are S and T connected by some path that avoids the failures. So the input for the decoder is the labels of S, of T, and of x1 up to xf, and the output should indicate the connectivity between S and T in G minus the failures. So for example, if the query is as depicted here in the picture, the answer should be 0 or disconnected. And note that F, the number of failures that we should tolerate, is a parameter which is a part of the problem definition. So let me briefly discuss some prior work. The first explicit introduction of this notion, also known as forbidden set labeling, was in 2007, and since then most of the work was focused on this problem when the graph comes from some special graph family, like planar graphs or bounded tree-width graphs. However, our focus is on the unrestricted case, where the input graph could be any undirected graph on n vertices. So the first work on general graphs was by Dory and Parter only recently in 2021, and they considered the setting of having at most f faulty edges rather than vertices. So note that in this variant, one should also give labels to the edges. And Dory and Parter gave two randomized schemes with short labels, where queries are answered correctly with high probability. And in a subsequent work from 2023, Izumi et al. Gave a deterministic construction by de-randomizing the approach of Dory and Parter with the cost of slightly larger labels. And here and throughout the talk, the O tilde notation hides polylog n factors. So by now, the labeling problem of connectivity under edge faults is relatively well understood, but in contrast, when it comes to the vertex failures case, we know much less. So in a previous work from 2022, we gave a scheme with polylog n bits that just supports up to 2 vertex failures, and also a scheme with much larger labels for the case where f is greater or equal to 3. So this raises a natural question of whether we can achieve labels of similar length as in the edge fault case, also for the vertex faults case. That is, can we give labels of length polynomial in f and log n for connectivity under f vertex faults? And in fact, even giving labels with polylog n bits for any constant f, which is greater than 2, was entirely open. Another related area of research concerns centralized data structures, or oracles, for connectivity under vertex faults. And here one should pre-process the graph into some compact data structure that can quickly answer connectivity queries under vertex faults. And in this setting, sometimes the query phase is separated to an update where only the faults are revealed, followed by a connectivity query where the source and destination are provided. And in a sense, the labeling problem is about trying to evenly divide a small space oracle into n small drawers, which are the labels for the vertices, so that one only needs to open the drawers of S, T, and X1 up to XF in order to answer the connectivity query that they form. So unlike the distributed labeling counterpart, this centralized version of the problem has been extensively studied, and it is very well understood by now with some conditionally optimal bounds, as demonstrated here in the table. So we also see that there is a gap between the centralized version and the distributed version of the problem. So what's the challenge in vertex faults rather than edge faults, which we understand pretty well? To sum it up in one letter, it's delta, the maximum degree in the graph. So the challenge comes from high degree vertices. And one way to see this is trying to use the short labels we have for faulty edges in order to also support faulty vertices. So in this matter, we can immediately get labels with length which is roughly delta, because every vertex can store the labels of all its incident edges. But the problem, of course, is that high degree vertices now need to store many edge labels and their own label becomes too large. So this is one way. And another way to see the challenge is by considering how the graph breaks after a fault. So if you have one edge fault, the number of connected components can only increase by 1. But if you have one vertex fault of a vertex with high degree, this can increase the number of connected components arbitrarily. So intuitively, vertex faults can make more of a mess in the connectivity structure of the graph. So our results bridge these gaps between the edge faults and vertex faults and between the centralized and distributed variants of the problem. So our main contribution is in providing labels for connectivity under vertex faults whose length is polynomial in f and log n. And specifically, we give a randomized scheme where the labels have length O tilde of f cubed, and also de-randomize it to get deterministic labels with length O tilde of f to the 7 bits. So in addition, we also show that these labels yield compact routing schemes, which allow passing messages in a distributed network from a source node to a target node, even when many vertex faults occur. Additionally, on the lower bound side, we provide a lower bound of omega f bits for the required length of the labels that holds even for randomized schemes, and this gives a separation from the edge faults variant. And also, we show that the seemingly very similar problem of deciding if the f vertex faults cause the graph to be disconnected, meaning if they form a vertex cut, is in fact harder and require much larger labels whose size is at least exponential in f. Okay, so in the rest of the talk, I'll mostly focus on our main result, and this is the randomized construction of the labels and how it works. So at the macro level, our approach is based on extending and combining two main techniques. The first is the linear graph sketching technique, which is applicable in many algorithmic contexts and was proven useful for labeling by Dory and Parter in their work on edge faults. And the second ingredient is the low degree decomposition, which is a technique that was developed by Duan and Petty in the context of centralized oracles, which precisely aims to mitigate this degree challenge of vertex faults that was discussed before. So the graph sketch technique was introduced by Ann, Guo, and McGregor in their seminal work from 2012 in the context of streaming algorithms. I'll present here a formulation which is more suited for our labeling problem. So here, each edge of the graph will get a randomized bit string, which we will call its sketch, and it consists of polylog n bits. And then we extend the definition of sketches also to subsets of edges and of vertices. So the sketch of an edge subset is just the bitwise XOR of the sketches of all its edges. And for a vertex subset, like U, here in the picture, its sketch would just be the sketch of its outgoing edges. So this is how we define sketches also for subsets. And this definition ensures a crucial property of the sketches, which is that they are linear, meaning that they respect the XOR operation, which is interpreted both as symmetric difference of sets or as bitwise XOR of strings according to the context. So now comes the key property of the sketches, which originates from the randomized construction, and it is that they enable detecting outgoing edges. So given the sketch of a vertex set U, we can extract from it some edge E that is outgoing from U with constant probability. And in fact, the sketch supports log n independent trials for identifying such an edge. So as we are dealing with vertex faults, we don't want the sketches to give us edges that touch the faulty vertices. So we can easily achieve this by using a technique called fault tolerance sampling. And this works as follows. For f-squared iterations, we generate a random subgraph gi by failing each vertex independently with probability 1 minus 1 over f. And then we simply concatenate the sketches with respect to all these gi's to get our new fault tolerance sketches, which consist of roughly f-squared many bits. And these new sketches remain linear, and we now get the ability to detect non-faulty edges. So now if we have the sketch of a vertex set U, and we also know of some set F of at most small f faulty vertices, then we can extract from the sketch of U some edge which is both outgoing from U and doesn't touch any faulty vertex. And this is because with constant probability, there will be an iteration where we failed all the vertices of F, but did not fail the endpoints of E. So now we can outline the first order intuition of our labels construction, which is the case where the graph G comes with some spanning tree that has low degrees. So in this case, we can use a sketch-based approach similar to Dorian-Pater in order to get labels whose length depends on the maximum degree in the tree rather than in the graph itself. So when the faults occur, this tree T gets broken into pieces. And our first goal is to compute sketches for those pieces. So let's demonstrate how we can do this. So let's consider this first piece that is rooted at the root of the tree, which will denote by R, and all the vertices are its descendants. And now let's locate these two faults X and Y, which are the faulty vertices that are sort of immediate descendants of R, in the sense that there are no other faults on the path connecting them to R. So note that the piece of T that is rooted in R consists exactly of those vertices which are descendants of R, but not of X or of Y. And therefore, in terms of XORs of vertex sets, we can express this piece PR as the XOR of the descendants of R with the descendants of X and the descendants of Y, which are denoted here by VR, Vx, and Vy respectively. So now we can use the linearity of the sketches, and this gives us a way to express the sketch of this piece, PR, by XORing the sketches of the descendant sets. So in order to support this sketch computation, we need to somehow find these sketches on the right-hand side. So what we do is we let X and Y store the sketches of their descendants in their own label. And we also make sure to store the sketch of VR, which is actually all the vertices, in every label. In every label. So this will give us a way to compute the sketch of the piece PR. So let's quickly do another piece, the one that is rooted in the child of X, which we denote here by X1. So again, we start by considering all its descendants, and then we look for this faulty vertex Z beneath it. And the piece rooted at X1 consists of the descendants of X1, which are not also descendants of Z. So we can express this piece as the XOR of Vx1 with Vz. And again, apply linearity of sketches to get this formula for the sketch of the piece. And the sketch of Vz will be stored in the label of Z because we already require that the faulty vertices store sketches of descendants. But now we also need to obtain the sketch of Vx1. And this means that the label of X should also store the sketch of Vx1. So what this means is that a faulty vertex should store a sketch also for each of its children. And hence, a label stores about delta T different sketches, which is affordable when T has small degrees. Okay, so we continue in this manner, and you can use the labels to compute all the sketches for these different pieces. And now, what we do with these sketches? What do we do with these sketches? So after we've computed them, we use them to run a version of the Borufka algorithm in G minus F. So initially, we have this partition of G minus F into these connected pieces, and then we use the property of the sketches to identify outgoing edges from the pieces. So from each piece, which is not already a maximal connected component in G minus F, we have some constant probability to find an outgoing edge. And these found outgoing edges connect between the different pieces, and our goal now is to merge the pieces along them. So in order to implement the merges, we again exploit the linearity of sketches. For example, we see that these three orange components need to be merged together, and we want to get a sketch for the new merged piece, so we can do so simply by XORing the sketches of the pieces that are forming it. So after these merges, we get a new partition, which is a coarsening of the original partition, denoted here by the colors. And what we can do now is we can repeat this process roughly log n times, and then what we can show is that with high probability, the partition we end up with actually corresponds to the maximal connected components of G minus F. So let's assume in this example that the colors here already express these connected components of G minus F. So the final step in order to answer the query is just to locate S and T within the original pieces, which is easy to do using standard tree labeling techniques. And then we simply see if these pieces ended up in the same big piece and answer the query accordingly. So in the example here, they ended up in pieces of the same color, meaning that S and T are connected in G minus F. Okay, so now we have our first order solution that uses a low degree spanning tree, and I'll try to give some rough explanation on how we enhance the ideas we've used here to solve the general case. So of course, the problem with the general case is that we don't always have a spanning tree with low degrees. And this is the place where the second main technique of a low degree decomposition comes into play. So the intuition is that the low degree decomposition gives us a way to reduce a general instance to the case of a low degree tree that we've seen before. So what does it do? Basically, it partitions the vertices of the graph into parts, and this partition has several important properties. So first and foremost, each of the parts is spanned by some low degree tree, where all the degrees are in fact constant. And second, the interaction between the parts is encoded by a hierarchy structure, namely a virtual tree whose nodes are the different parts. And this hierarchy satisfies three important conditions. First, it's shallow, meaning there are only log n levels. Second, the edges of the original graph G that cross between different parts respect the hierarchy in the sense that they only go between parts that have ancestry relations in the hierarchy. So intra-part edges can go only vertically in the hierarchy and not laterally. And finally, if we take any sub-hierarchy, then the vertices that belong to parts in this sub-hierarchy induce a connected subgraph of G. Okay, so now I'll try to explain how we use this low degree decomposition. So first, as a pre-processing step, we use the decomposition to add some additional shortcut edges to the original graph. So what we do is we go over each sub-hierarchy and find all the vertices which are neighbors of it, meaning all those vertices in the parts that are above the sub-hierarchy and that have edges going into it. So what we do is we add a clique of shortcut edges, which are new edges that were not in the original graph, between all these vertices. And such a shortcut edge represents the fact that one can travel between the endpoints of this edge through a path whose internal vertices all lie in this sub-hierarchy. And this is because the sub-hierarchy induces a connected subgraph. Next, the query arrives, and when this happens, we divide the parts of the decomposition into affected and unaffected parts. So the affected parts are those that either contain a query vertex or that are found above parts that contain query vertices. And this definition ensures that if a part is unaffected, then all of the shortcut edges that we created for the sub-hierarchy beneath it are valid in the sense that they represent non-faulty paths in the original graph. So we can therefore prune or discard these unaffected parts as the connectivity through them is already encoded by the shortcuts. And now, the faults break the low degree T's of the affected parts into pieces, so we can employ a similar strategy as we saw before in the low degree tree case to store sketch information of descendants in the trees, and then use these to compute sketches of these pieces. Here we also take advantage of the fact that the hierarchy is shallow, so some affected parts actually remain as a one single piece, but then the query vertices beneath them have the budget to store their sketches because there are only log n parts above every vertex. So finally, to answer the query, we run the Borufka procedure using the sketches, starting from these pieces of the affected parts. And here we remark that the outgoing edges we get from the sketches might in fact be these shortcut edges that we added that correspond to paths through unaffected components. But on the flip side, we must employ some mechanism to avoid getting shortcut edges that correspond to affected sub-hierarchies, because these ones can be invalid and they can actually represent paths that go through faults. So here we crucially use the fact that the hierarchy ensures no lateral intra-part edges and that we added these shortcut edges to argue about the correctness of the Borufka algorithm, meaning that at the end of the Borufka, we can check if S and T ended in the same piece, and this will imply whether they are connected or not in the original graph G. So to conclude this overview, let me just mention that there are many technical difficulties that I swept under the rug, and I want to shortly address them now. So the main issue is that the low degree hierarchy of Duan and Petty is actually not sufficient to be used as is. And there are two inconvenient properties. First, the low degree trees for the parts might actually be Steiner trees that also contain vertices that are not in the part. And second, and although this is a bit subtle, this is even a more crucial point, the size of neighbor sets of sub-hierarchies may be very large. And this really hurts the label size required to support the sketch computation. So to get over these problems, we develop a new low degree hierarchy using the, sorry about this animation glitch. So to get over these problems, we develop a new low degree hierarchy using the Duan-Petty decomposition as a starting point. And then we tackle exactly these two issues. First, we can settle for logarithmic degrees in the trees instead of constant, and then we show how to eliminate the Steiner vertices from the tree. And second, to solve the second challenge, it requires settling even more. And in fact, we will allow some vertices to have arbitrarily large degrees in the trees of the decomposition in order to obtain small neighbor sets. And this seems a priori very problematic because then we could have failures of vertices with large degrees, which is exactly what we wanted to avoid in the first place. And the trick to get around this is in fact to generate several different hierarchies with the property that for every possible set of faults, one of these hierarchies is good, namely it gives low 3 degrees to every vertex in F. So let me conclude. Our main result is providing labels of poly F log n bits for connectivity under F vertex faults in general graphs. And in terms of open questions, there are many interesting ones. So first, can we go farther from reporting connectivity and report approximate distances after vertex failures? And also a similar question holds for the routing schemes that support vertex failures. Can we provide such routing schemes with good stretch guarantees on the routes? And such distance labeling and routing schemes for edge faults were provided by Dory and Parter, but for vertex faults, we still don't have ones. Also, an interesting question concerned these cut labels that I mentioned. We gave a lower bound, which is exponential in F, but we still didn't show a matching upper bound. So this is also interesting. And lastly, what about having smaller polynomial in the size of the labels? So especially in the deterministic construction, the size we provide is a rather large polynomial in F and log n, and there seems to be some room for improvement. Okay, so that's it, and thank you for listening.